had the exam last night, and I was just so delighted that everybody did such a great job following directions, going to the right room. We handed out the exams in even more record, even faster than we did the last time. So, and also, you know, thanks a whole lot for not sending me a zillion emails before the exam. I started to think, wait a minute, what's going on? Do they know there's an exam? I'm not getting any emails. You know, until like maybe an hour or two before the exam, I hardly got any emails. And usually it's, you know, my inbox is flooded. And the stat inbox was not flooded. And I said, wait a sec, I got nervous. So I sent you out that email just to remind you there's an exam. I thought, well, maybe everybody forgot or something. But you didn't forget, you just know what's going on. And you're doing something right that no other class has done before. I haven't quite figured out why that is. So that's interesting to me. Now, today, what we're going to do, and I'm glad you all came today after the exam, because it's always an important class because we start a new section. And of course, there's going to be iClicker points always right after the exam. So that'll be towards the end of the class. Now, so we did a little bit of probability, and now we're going to apply it. We're going to translate different situations into probability models so we can do inferential statistics. That's the plan. So let's look. There's an analogy between many chance processes and drawing numbers randomly from a box and adding their sum, or taking their average, or if it's finding out the percent, if it's a box that has ones and zeros, the percentage of like yes and no's. In this chapter, we're going to just deal with gambling games because they're the simplest chance procedures. They directly to analyze the statistics on because they directly translate into probability models. So that's what we're going to do first. And then later we're going to look at sampling processes like taking public opinion polls. We're going to look at how to analyze results from randomized experiments and so forth. But first we're going to start with the simplest, most direct usage of these probability models. Okay, so what is a probability model? It's just a box. The simplest one, the one that we're going to use for this course, is just a box that has tickets in it, and each ticket has a number written on it, and you specify how many draws are going to be made from the box and with or without replacement. It's really pretty simple. But the easiest, sometimes it can get it can get complicated if you don't break it down by making the model just thinking of just one draw, not 1,000 draws or 100 draws, just thinking about what happened on the first draw and making the model for that. That's a hint, and it makes it much easier. I'll show you why. So in creating a box model, it's always simplest to start by making the box for a single draw. And then you think about what the numbers need to go into the box, etc. All right, so we're going to start really, really easy. Suppose you didn't have a coin with you and you wanted to create a box model for counting the number of heads in 100 tosses of a fair coin. So this is a chance process. Every time you flip a coin 100 times, you're going to get something different, right? There's chance variation. So let's just, instead of doing the real situation where we had the coin, let's create a box model for it. Okay, so first, start with, you see this 100 draws, but first, just, that pen already ran out, sorry. Try this one. First, start with a single, just a single toss, okay? A single toss, let's think about that first. So you have a box, and the coin can either flip, and has tickets in it, so we're just gonna make these square tickets, and The coin can either, when you toss it, land heads or tails, okay? So that's the box for a single draw. You could either get one head or one tail, right? But the box each ticket has to have a number written on it. So we don't have numbers there, we have letters. All right, so we're just gonna have to translate these into numbers. So we see what we wanna do. We wanna count the number of heads. So just think about one toss. In one toss, you could either get a head, in which case we'd count it as what? How many? We're counting the number of heads, so we'd count it as what? One. And if you got a tail, you would count it as how many heads? Zero. So if you're counting heads, that's what you do. This is one head, and this is 0 heads, one tail, which is 0 heads, because we're just counting heads. If we were counting tails, it would really be the same picture. We'd have 1 and 0. We'd just say one tail and 0 tails. Okay, so that's our box. So instead of, if you didn't have a coin and you wanted to do the same thing, heads or tails, you could just shake that box. And if you got a 1, you got a head, and if you got a 0, you got a tail. Or if you wanted to count up to see if it was count up the number of heads you'd get in 100 tosses, you'd just draw from here, from this box. How many times? You would draw from this box. Getting rid of that pen, sorry. Always put them back and then, thanks. Okay, so you draw from this box, right? What, 100 times. Now obviously if you're going to draw 100 times from this box, doesn't it have to be with replacement? After 2 times you wouldn't have any tickets. But more importantly, even if I had 100 tickets in here, I'd still want to do with replacement, because a coin doesn't change, it has no memory, it's going to be the same every time. So you want the chances of getting ahead to be 50-50 every time. So you draw 100 times with replacement, and then we're just going to count and sum the number of heads, the number of ones we get, right? We'd get a 1, if we, you don't have to write this down, but let's say, oh, we got a 1, we stick it back. Then we get a 0, we stick it back. Then we get a 1, we stick it back. Then we get another 1, a 0. We'll just count up in 100 times. We'll just count up how many ones we got. All right, take the sum. You're just going to take the sum of all that. So you might think, well, okay, that's all right, but why, since we have 100, draws, why don't we just put 100 tickets in the box? How does it really make it simpler to just put 1 and 0 in there? Well, one way it makes it simpler is you just have to draw 2 tickets instead of 100 tickets. But if you could, you don't have to write this down, but there'd be nothing wrong with putting 100 tickets in the box. And if we did that, how many ones would we have? I don't want to draw out 50 ones. We'd have 50 and 50. And then when you draw from here, wouldn't it be the same thing as drawing from that box? Wouldn't it? But the temptation is, when you have this box, you could do this, and I wouldn't mark it wrong. You could still draw 100 times, but the danger is when people see all these tickets, sometimes they don't remember that you still have to draw with replacement. Why? Why? Well, if you didn't, for one thing, wouldn't you always get 50 ones and 50 zeros? So it wouldn't really be like a fair coin. A fair coin is a chance process. It has variation. you wouldn't have any variation. You'd know what you'd get. You draw everything. You might as well just dump the whole box out and count your ones and zeros. So it's not. And also, even if you didn't draw 100 times, let's say you just drew 2 times, and let's say you got ahead, and you didn't replace it, well, then what would be your chance of getting ahead the next time? You want it to be 50-50, but it wouldn't be anymore, because now you'd only have 49 heads. So your odds of getting ahead would be less. So it always has to be with replacement if it's a fair coin. So that would be okay, but let's keep it simple. It's so much easier to think about. All right, any questions on that? So let's just do the next one. All right, now let's create a model, a box model for counting the number of 2s that appear in 200 rolls of a fair 6-sided die. So with a fair 6-sided die, as you all know, it's gonna look like this. You have 1, all with equal probability. You can get 1, 2, 3, 4, 5, and 6, all with equal probability. Now, let's be a little careful and let's think what we want to do. We're going to create a box model. Should I just put in, I'm going to have 6 tickets. 1, 2, 3, 4, 5, 6. And you might think, oh, why don't we just 1, 2, 3, 4, 5, 6. Well, does that fit what we want to do? What do we want to do? We want to create a box model for counting the number of 2s that appear in 200 rolls of a die. Okay? So think about just doing it the first time. Make the box for just a single. This 200 gets too confusing, so just make it for a single roll. And let's think what can happen. You're counting. So if you get a 1, what are you going to count it as? 0. Why? You're going to count it as a 0 2s, right? That's what it is. All we care. What if you get a 2? How many are you going to count that as? 1. Yeah, we got a 2, so we're going to count it as 1, 2. And what about all these? If we get any of these, are we going to count? We're only counting the number of 2s. So if we get these, are we going to count them? So all these will be zeros because they're all what? 0 2s. So our box is just 1 1 and 1 0. Or a shorthand way of writing the same thing, because you're going to get tired of writing all these boxes. So a shorthand way to write the same box that we can use, we'll just say, okay, these are the 2 types of tickets. There's a 0 and a 1 in this here. And we have how many zeros? 1, 2, 3, 4, 5 of these. So we can put a little 5 on top. Or you could put it on bottom. It doesn't really matter. Just put either above or underneath. And then just one of those. So that shows that there's 6 tickets in the box, 5 zeros, and 1 1. I'll make it look like that. All right, so we can do that. Now we've got the box for a single roll, and that's not what the question says. We also have to, we just did the first part of the question. We specified, we just did this. Now we have to say how many draws should we draw from here. If we really wanted to do this, we want to count the number of 2s on 200 draws. So we're going to draw from here how many times? Draw what? 200 times. And we have to specify without or with replacement. It's going to be with replacement. And what are we then going to do? And then we'll sum up all the ones we get. And sum up all the draws. The ones and the zeros. We'd expect to get what? What would you expect to get? Would you expect to get 100 ones? No. Wouldn't you only expect 1 out of 6 of them to be ones? So you'd expect to get about 1/6 of the 200 to be ones. Any questions on that? All right, so we're almost done with this chapter, but we're going to do 2 chapters today. We're going to do 1.5 chapters today. All right. So a multiple choice test has 25 questions, and each question has 5 answers. Suppose you guess at random on each question, and your number of correct answers is counted. What would be the box model? Well, hint again, this hint really helps you here. Always make the box for what? A single play, a single question, a single toss. Okay, whatever you're dealing with, a single question. So start with just one question. Okay, you have one question on a multiple choice test, and each question has 5 answers. So how many? There's 5 choices, 5 options. You know, like on our exam last night. 5 options, only one of which is correct? Yeah. A lot of mine, so pretend like the exam last night, you know, had 25 questions and it was multiple choice. Okay, so each one has 5 options you could circle, so there's going to be 5 tickets. And if you're really guessing at random, which you probably did on some of those questions, maybe you could eliminate some. Pretend this is one where you really have no clue, so you're just saying, okay, blindly guessing. So there's only one right one. It would be like, you know, shaking up this box that had one right answer, and all the rest you'd get 0 credit for, and just picking from that box. Wouldn't that be the multiple choice? Isn't that the same as just guessing on a multiple choice? Okay. So this is like, if there were 25 questions and you wanted to see what your score would be, this would be like drawing 25 times. Each question's the same, with the same format, so it would be with replacement, and summing up all the ones, counting the number you got correct. I mean, you'd count the zeros too. You'd get a lot of zeros. 4/5 about would be zeros, but they wouldn't enter into your score. You just count up all the numbers, sum up all the numbers you get. And you wouldn't do very, I mean, chances aren't of doing very well. Later we'll look at what's the chance that you could actually get half of them right, pass a test like that just by guessing. Because you'd expect to get only 1/5 of them right. We're going to look later at, like, if you really did that, what would be the chance of you actually passing? And in fact, on our finals, it's interesting, because our finals are Scantron, and I usually have 5 questions, 5 options for each of the 100 questions. And some people actually do worse than chance. They get less than 20 right. Like if you imagine if you had 100 questions and it was this format, then 1/5 of the 100 you'd get right just by the luck of the draw. But a few people sometimes do worse than luck. It's kind of sad, isn't it? So I sometimes run their exams through with a different form, and sometimes they do better with a different form. It's not, I mean, they certainly, I don't think they cheated off the right form. I think they just, you know, you don't always get the expected value. Sometimes you get more than chance, sometimes you get less. They were just guessing on everything, and they did worse than chance. Okay, now, how many of you have ever played roulette? Raise your hands. Well, a roulette table has 38 slots, and since I've figured you don't go gambling much, are you, that's not even legal anywhere. Is it legal in Illinois anywhere? But you have to be 21, right? So some of you probably legally. But I brought in a little gambling roulette wheel here, so you can see what it looks like. All right. So you can read along in your books, but it says that a roulette, first let me just show you what you do. What you do is, the game is you pick a number or a color or a set of numbers, and then you spin this, and if your ball lands in the one you picked, you win a certain amount. So, for example, you can write down a bet. Go ahead, just write down a bet. Write down a number, see if it lands on your number. Okay, just for fun. Okay, everybody have a number? There's 38 numbers, okay? You can pick these, there's 36 numbers, but then you have this 0 and the double 0. So that adds up to, because I think the highest number here is 36, right? I don't even see it, but you can probably find it. There should be a 36, right? Does anybody see it? What color is it? Oh yeah, red, there. And the lowest number, so it's 1 through 36, and then you have these two green ones. That makes 38 numbers. Okay, so let's see if you bet on it. See if anybody, oh come on, don't get stuck on me. Double 0. Did anybody pick double 0? You know what that would mean? If you bet $1, I would have just, I'm the house, I would have just cleaned up. I would have gotten all your money. If you think about that, there's about 300 people. That would have been easy 300 for me. Now, let's do a different bet. How about bet on a color? Now there's 18 of the reds, 18 of the blacks, and then there's 2 green. So bet on a color. No, you wouldn't bet on green. It pays 50-50. You'd have a better chance. You bet on red or black. Okay? Watch, it's going to land on green. Okay. Black. Okay, how many of you won? And how many of you lost? Oh, I think I would have lost money. It looks like more people bet on black than red. So I would have lost money that time. Okay, now, well, we have to figure this out exactly, though. We're just guessing. This is much more fun to do. Let's just do one more and write down another number. No one won that time. Come on, let's see if anybody has a lucky number. $34. Anybody get it? Yoo-hoo! You got 34? Yeah. Great, okay. Lucky day. Now, not that you're going to win anything, but still. Okay, so now we're going to learn about how to actually figure the odds in roulette. So, all right. First, let's create a box model for it, because it'll be a lot easier to then figure out the probabilities. So a roulette table has 38 slots, as you saw. 18 of them are red, 18 are black, and 2 of them are green. If you bet $1 on red and it comes up red, then you win the $1. Otherwise, you lose. What's the box model for your total winnings playing roulette 50 times betting $1 each time? Now, make the box for a single play. Okay, just one time. All right, so here's the box. And what can happen? You can either, if you bet $1, you can either win $1 if it comes up red. So you could win $1, right? And what's the only other thing that can happen to you? Lose $1. You can't break even here. You either win $1 or you lose $1. Because you pay the $1 and they'll take it away if it lands, what are you betting on red? If it lands black, they take it away. You've lost your $1. If it lands red, well, you get that dollar back. That's just breaking even. But they, you give you a dollar. You didn't win anything yet. They'll give you that back. But then they give you a dollar. So you either win or lose. No way to break even on any roulette bet. You either win or lose. So there's just a positive and a negative one. You win or you lose. Nothing else can happen. All right. Can you see that negative? That's a negative there. That means losing a dollar. Now, how many slots are there? There's 38 slots. So we should have 38 tickets in here. Because the ball could land on any one of the 38. And how many ways are there for you to win? 18. Why? Because if it lands on red, and there's only 18 reds, so yeah, there's 18 ways for you to win. How many ways are there for you to lose? 20. That's why the house has the edge. You see, you lose if it lands on black, but those 2 extra greens are to the house's advantage. There's 20 ways for you to lose. So that's why the house always has an advantage. Otherwise, it'd go out of business if it was 50-50. The odds are always for the house. That's how they make money. It's not gambling for the house. If they deal in big enough numbers, the law of averages, the law of large numbers will guarantee pretty much that they're not going to lose. They make a lot of money. Particular individuals of you gamblers can win, but as a whole, you're going to lose. All right. So now let's draw 50 times from the box. 50 times with replacement, and take the sum of the draws. And we'll see, how likely, if we have time today, we'll see how likely it is in draws like this, how likely it is that you'd win, what are the chances that you'd win a certain amount of dollars, what are the chances that you'd lose, etc. More ways to lose, but you still have good chances of winning. Okay, how about this bet now? A roulette table has 38 slots, the same thing, but now what if you bet on a number? On the number 7, and it comes up. Then you don't win a dollar, then you win $35. Otherwise, you lose a dollar. So different bets pay different amounts. Like if you bet on a color, that's even money. You win a dollar, you lose a dollar. Here, it's 35 to 1. So let's just we'll make the box again for the single play. We still have 38 tickets. There's still just two types of tickets. Either win or you lose. 2 types. Just 2 things that can happen to you. You either win some amount, we can put that in, or you lose. We'll put a negative sign. But now, what can you win? If you win, if it lands on that 7, what do you win? If you're betting a dollar, you win $35. That's a lot. And if you lose, you only bet a dollar, how much do you lose? You only put a dollar down, they take that dollar away. If you win, they give you that dollar back, which makes you break even, and 35 more. So that's the 2 things that can happen. And that looks great until you realize how many ways are there to win. Only one will play it. Only one way to win. And that's if we'll get $35. But we lost our dollar. What? And then you think, oh, come on, I have a few dollars. I'm going to play it again. Let's see. Come on, I want to. 35. What? 7. 7 is all we want. Ah. Well, you think, oh, just if it was just 1/3 of that. Come on, let's try it. This is our gambling mentality. I'm just 3 away now. And 21 divided by 7 was 3. This is a sign. Gotta play. Okay. 30. 3 times 10 is 30. That means I'm going to win 10 times more. Yeah, sign. I'm going to play. Yeah, it's telling me. Have you ever seen gamblers like, okay, I know it this time. All right. Maybe. 7. Think it. 21 again. 21. Doesn't that just, that's so close. There's that 3, 7 times 3. I think we have to play 3 more times. And you keep going, and you keep losing money. We have $3 more. We're gonna do it. Why that 35? Is it rigged? 2 more times. We just need a 7. Come on. 16. Okay. Last try. Let's all think 7. Otherwise, I'm going to walk out of here with not a penny. I just need it. Oh, why me? Okay, it's not just you, it's anybody. It's statistics, you know, your chances aren't very good. Okay, so let's think about it. And how many ways are there to win? Just 1. And how many ways are there to lose? 37. And we didn't do it 100 times, but you draw 100 times with replacement and take the sum. We could have won. And if we'd won, it would have been smart to stop because we would have had $35 in our pocket. All right, so now we're going to figure out what are our chances of winning if we did that, and what are our chances of losing, and so forth. So there's the summary. Any questions so far? One thing you might want to note is that unlike things we're going to look at in the future, like public opinion polls or a lot of different, the draws with gambling are always made with replacement because the dice, the coins, etc. give you the same chances each time. You know, the only exception to this is blackjack, where things change, and that's the only game you can really win on if you count the cards. These other ones, you saw how there were more ways to lose. The odds, the average of the box, the expected value of the box, you'll see what I mean in a minute, is always negative. That means the odds are against you. And the box doesn't change. The roulette wheel's the same every time. But in games where, like blackjack is the most famous one, where you draw cards out and you don't replace them. So if you're keeping track of all those cards, you can sometimes, have the odds in your favor. So you can win with blackjack. All right. Now, and of course with poker, if you know all the psychological elements that go into it and so forth. Anybody here serious poker players? There's a little cool, in the games, there's a little cool poker game that you might be interested in if you click on games where the money hall was. Once we get those Java applets working again, but if you go to Internet Explorer, they work there. And you can click on the poker games. Okay, now, what are we going to talk about here? Well, what we're doing here is we're going to look at what we would expect to get if we did these gambling games over and over and over again, and how much variability is there? What's the likelihood? What we'd expect to get something, give or take what, and what are our chances? You know what it's really similar to? It's analogous to the statistics we worked out earlier when we just had a set of numbers in front of us and it wasn't a chance process. Now we're doing the same thing for chance numbers. That's the way that you can think of it, statistics for chance numbers. Okay, earlier when we did these descriptive statistics, we just summarized a list of numbers by computing their average and their standard deviation, and then we did a graphical display with a histogram. Now we're going to do these analogous summaries for these numbers generated by gambling processes, by sampling later, by a lot of different numbers generated by any chance process that we can model with a probability model. So if you have, you draw n draws from a box, you might be interested in maybe the sum of the draws. You certainly would be if you were doing gambling like we were, or if you were guessing on a multiple choice test. You're interested in the sum of your correct answers. So here you'd be interested in the sum, this statistic, in gambling, or in guessing on multiple choice tests, things like that, which is basically gambling. All right? And later on, we're going to look at the average of the draws and the percentage of draws. When would we be interested in that? Well, let's say you took a sample, like in a public opinion poll. You took a sample from maybe 1,000 people, a random sample from all 130 million Americans who voted, a pre-election poll, and there would be interested in the percentage of voters, potential voters who said they were for Obama. So that would be a case where we'd be interested in the percent of the draws, or what's your opinion on gay marriage, or what's your opinion on the death penalty, or I could sample this class. Take a random sample of 100 people out of the 1,100 and say, what's your yes or no? Do you think I'm going too fast or too slow? Yes, if you think I'm going, do you think I'm going too fast? Yes or no, or something like that. Probably you think I'm going too slow. Now let's say average of the draws would be if I changed the question and said, on a scale of 1 to 10, with 1 being I'm going way too slow and 10 being I'm going too fast, what do you think? And it would be a chance number if I only took 50 of you had asked, or 100. These days I'm asking everybody in the anonymous survey, so I don't really have to do that. But let's say you were a random sample from the whole university, and I wanted to get a feel, not on that issue, but on maybe how students feel about the death penalty. And pretend you were a random sample from all how many students are there at this university? 35,000 or something? 40,000? So 1,000 students out of 40,000. And I wanted to, and you were a good cross-section because you're a random sample. Well then, I might be interested in the percentage of people who are for the death penalty. But if I asked you a question about I don't know, how much money do you think you'd like to make so that you'd consider yourself set for life or something like that, then I'd be interested in the average number. So for now, we're just interested in sums. Usually with public opinion polls, you're interested in averages or percents. So this is going to come up with surveys. Let's concentrate on sums now. All right, that's what I say here. In a much shorter way. I rambled. Okay, so the sum, and the average and the percent are going to vary because it's a chance process. Every time you draw a new sample, it's going to vary. Every time you spin this roulette wheel, it varies. Okay, let's see if we get our 7. It varies. Come on, 7, no. 14 twice. 7, no. All right, so we'd like a way to describe the distribution of all the possibilities that you could get and their likelihoods. So it's going to be a probability histogram. Instead of actually describing the data we have in front of us, we're going to draw a histogram. This is going to look very similar. It will sum to 1 and it will look the same way. But what it is instead is a description of every single possible sum that you could get. Let's say if you did this 10 times, every possible sum you could get, and their likelihood. Okay? And then what you would expect to get, that's called the expected value, similar to the average when you have a set of numbers and descriptive statistics, and how far off it's likely to be from the average, and that's called the standard error, which is analogous to what? What does that look like? Standard error. What does it seem like? For us, when we have actual numbers and we see how far off they are from the average, we call it what? The standard deviation. So this is similar to the average, the expected value. This is similar to the standard deviation. And then we're going to have a probability histogram that's going to be similar to our regular histogram. Okay, so let's get started. And computing the expected value. Okay, so this is not hard. Let's just start off real easy. Here's the formula for it, but it's pretty much common sense. The expected value for the sum of n draws made at random with replacement from a box is n times the average of the box. But you'll see it's pretty much a no-brainer why it's that way. Okay, so 100 draws are made at random with replacement from a box containing these tickets. And the sum of the draws is computed. All right, what do you think the smallest I could get? If I draw from here 100 times with replacement, it's really unlikely, but what's the smallest sum I could get? Right, I could get all ones. Really unlikely, but it's possible. So that would be 100 if I got all 100 ones. And what would be the largest I could get? 500. If I got all fives. But what would you expect to get? Okay, first we'll use the formula and then I'll show you why it makes sense. So the expected value of the sum of n draws, of 100 draws, well, I'll say n. Why don't I say in general? Of n draws is n times the average of the box. That's just what I said here. Okay, it's n times the average of the box. Nothing new there. All right, I just want to show you why it's true. First, let's just do it for this. Here, what's n? What's n? N is your number of draws, so here, this is n. So it would be 100. And what's the average of the box? What's the average of the box there? 1 and 5 is 6, 2 and 4 is 6. So we have 15 divided by 1, 2, 3, 4, 3. You can see 3's in the middle, so the average is 3. So it is 300. Okay, so that's the expected value. But another way to look at it is why this formula would work. Wouldn't you expect the same, that 1 out of 5 tickets would be a 1 and 1 out of 5 tickets would be a 2, etc. So you would expect, 20. Okay, so here, maybe the easiest way to do it is this. This is the same. I should have done it. Okay, so you have 100. We got this as the average of the box. So how did we get that? We said 1 plus 2 plus 3 plus 4 plus 5 over what? Over what? 5. Isn't that the average of that? So it's telling us that we'd expect 21s plus 22s plus 23s. Wouldn't you expect an even number of all that? So that's all it's doing. It's not mysterious. It's just saying you'd expect, 20 of each of these. All right, and that's 3. Let's move on. That's not hard. Okay, now, okay, we should do an iClicker pretty soon, but where should we do that? Maybe, let's see how far. I didn't post your homework yet. I got to figure out, we should still go a little further so we can, all right. A die is rolled 100 times. The sum of the number of spots is counted. What's the expected value? All right. So we have this die, and we have to be a little careful because when we do our box, because it's not going to be exactly the same box as what we did before. Let's check it out. All right. Think about it for a single time. We're going to have 6 tickets in here. Now, what are we interested in? The sum of the number of spots. This would be like if you're playing a Monopoly game or something where you rolled the die 100 times, and that's how many spaces you moved. You care what's on the dot, what numbers on the die. Before we were just counting, classifying. Is it a 2? Then we count it as 1, 2. Is it not a 2? We count it as 0. Now we're paying attention to actually, if it's 2, we're going to count it as a 2. We're summing. If it's 3, we're going to count it as a 3. That's what we're doing. We're counting the number of spots up. Maybe it's some game where you win money, depending on how many numbers are here, whatever. But the numbers matter now. Okay, so what's the expected value of the sum? The expected value of the sum is just going to be n times the average of the box, which is equal to what? What's n? 100. That's the number of times. That's n. And what's the average of the box? Can we just, it's going to be right in the middle there, right? Because there you times 3.5. So we'd expect to get 350. Okay? Now let's do this one. You bet $1 on red. What's the expected value of your winnings in roulette? Let's try this one. Okay, remember, what do we have here? 18 reds, 18 blacks, and 2 greens. Okay, so let's make the box. It's on red, so you either win $1 or you lose $1 because you're betting on red. So you either win $1 or you lose $1. All right, and there's 38 tickets, and if it lands on red, we'll win. If it lands on black or green, we're going to lose. All right, now, what's it asking? If we actually did this 76 times, well, we're going to expect to lose, right? Because there's more ways to lose, but how much? So remember, the expected value of the sum is n times the average of the box. You know, it's just saying on the average you're going to get what's in the average of the box. N times is what? What's n in this case? How many times they're playing? What's n? That's how many times? 76. What's the average of the box? Let's see. It's going to be negative always. So the average of the box. Let's sum up all these. We'll sum up the 18 ones plus what? The 20 negative ones. We sum up 18, and 18 of those cancel out to 0. We have 2. 18 minus 20. Negative 2. Negative 2 what? The average is out of 38. So that's the average of the box. It's about negative a nickel. On each $1 that people play in roulette, the house wins about a nickel. All right, that's about a little more than a nickel. Okay, so we're going to multiply that. And we get negative $4. So that's not bad. I mean, if you wanted to spend an evening gambling, you'd expect to lose only 76 times. That's a lot. Maybe that's worth it. $4 worth, and think about it. You could win big, maybe, or lose big, but that's the important thing that you're interested in. Like, should I spend yeah. First of all, it wouldn't be fun if it was just $4 and you knew you were going to lose the $4. The fun is, how much could you win and how much could you lose, and what are the chances of that? And that has to do with the variability, the standard deviation, the standard error. So that's what we need to figure out next, the standard error, to do anything interesting. So, computing the standard error. right. So the sum of the draws from the box will be around its expected value, but do you think if we really did that, I mean, it wouldn't be gambling if you always lost $4. It's going to change. And so we want a way to describe the variability. We want, to put a give or take number on that $4, loss of $4. So the likely size of the chance error, it's given by the standard error. It's very similar to the standard deviation. In fact, it depends on the standard deviation of the box and on how many times you play. So the sum is going to be its expected value plus or minus some standard error, right? In the last case, it was going to be you play 76 times, you expect to lose $4, give or take something. So this is what we got to figure out. And this is very important square root law that I'll explain. I can prove it in the notes. I don't want to do the mathematical proof here. I mean, in the online, you can see a mathematical proof. I don't want to go through that here, but I want to give you an intuitive proof here. So the standard error, or at least a way you can think about it, the standard error of the sum of n draws depends on two things. The standard deviation of the box, standard error and standard deviation, and how many times you play. Think about it. Think about it. Let's just go back to this box. Standard deviation of this box. Let's say this box had all ones in it. All ones. Both numbers were 1. Every number was a 1. The standard deviation would be 0, right? The average would be 1, and the standard deviation would be 0. There'd be nothing chancy about it. You draw from here and you'd get a 1 every time. So if we drew from here 76 times, we'd get 76, and we'd have no variability. So when your standard deviation is really low like that, you're going to have no variability. Now, on the other hand, let's say it was, instead of 1 and negative 1, it was $1 million and negative $1 million. That's a huge standard deviation, a huge spread. Huge spread. So then what would you expect? You expect 18 million minus 20 million, negative 2 million over 38. That's what you would expect. But there's a huge standard deviation there. You could win $1 million or lose $1 million. So the standard deviation of the box increases the error. There's more variability. If there's more spread in the box, and you don't know what you're going to get, you could get something really high or something really low. Of course there's more variability. All right. Now, so that's why your give or take depends on your standard deviation of the box. Now, why does it depend on n? Well, think about it. This is like chance error. Each time you play, you're introducing more and more error, right? It's a chance process. So each time you play, you're adding, you're increasing the chance error. But why doesn't it just scale as n? Why the square root? And the basic way you can think about it intuitively is because sometimes the error is going to go in your favor. You're going to win more, and sometimes you're going to lose. And the positives and negatives can cancel out somewhere. So it doesn't really scale as n. It would if all your error was always in one direction. But since it's positive and negative, they can cancel out. So you can get, so because of that, and I can explain it, why mathematically that works out to the square root of n. But you'd expect to have more error. They're not going to cancel out exactly. You'd expect to have more error, and since there's positive and negatives, it scales as the square root of n. So that's the intuitive explanation. So how does this work? So let's go ahead and notice that as the number of draws increases, so does the standard error, but not as quickly. So the standard error of 100 draws will only be 10 times as large as that of 1. 100. Square root of 100 is 10. All right, so I have a proof of that online. Now, let's do an example. All right, so example 4, let's look at this. So a box contains these tickets right here. Compute the expected value and the standard error of the sum of 25 draws. How are we going to do that? Well, the expected value of the sum is going to be n times the average of the box, which is what? What's n here? 25. And what's the average of this box? Can we see this? The average of that box, what do we have? 8 and 12 is 20 divided by 1, 2, 3, 4, 5. The average of the box is 4. So we'd expect to get 100. Give or take what? We draw from here 25 times. Pretend this was money. We'd expect to get 100, but give or take what? Well, we know we could get as high as low as only $25, or as high as 7 times 25, but what would we expect? So let's do the standard error of the sum, and that's the square root of n times the standard deviation of the box. So that's the square root of 25 times the standard deviation of this box. Is it okay? Do we want to do that now? Can I just, you want me to calculate that? Okay, we could. So what are we going to get? So we'll see. So we have to take the deviations. So you say 1 minus 4 is negative 3. 3 minus 4 is negative 1. I'm taking the deviations. 4 minus 4 is 0. 5 minus 4 is what? 1. And 7 minus 4 is what? 3. Now, what do I want to do with all those deviations? First of all, check, do they add to 0? Yes. So now we want to square them. And take their what? Average. And then their square root. So what does that give us? 9 plus 1 is 10. And here we have another 9 and 1 is 10, so we get 10 plus 10 is 20 over 5. So we get 2. That's our SD. Okay, so we're going to multiply that by 2, and what do we get? 10. All right, so you'd expect what? To get 100, give or take 10. Now, let's try the same box, but now let's do it 100 times and see what happens. So same box, but now let's draw 100 times and see what happens. I want to see what happens to this. Okay? So look what we're doing. If we draw 4 more times, what's going to happen? All right, so we have the same box, same average, equal to what? We're drawing from the same box. I can pick, it's this box. And the same SD, what's that? Same SD is equal to 2. We have this same box here, I can picture it. 1, 3, 4, 5, and 7. That's what we're doing. But now n is equal to 100. And here, n was equal to 25. That's the only difference. All right. So now what should we do? Let's do the same thing. Expected value of the sum is now, instead of 25 times 4, it's going to be what times 4? 100 times 4. So we get 400. Well, that makes sense. Doesn't that make sense? 4 times as many draws, 4 times the sum. But watch what happens to this standard error. This is why I'm showing you this. The standard error is not going to be 4 times as big. The standard error of the sum is what? Instead of square root of 25, what are we going to have? Square root of what? 100. And that's, watch what happens, times 2. And so that gives us square root of 25 and square root of 100. This is 5. What's this? It's not 4 times as big. What is it? It's only the square root of 4 times as many big. You see, you can write this as the square root of, this is the same thing as the square root of 4 times 25. So you see, it's not going to increase by 4. It's going to increase by the square root of 4. So it's not, that's the same thing. So you're going to really, it's only going to, it's only going to double. Square root of 4 is 2. All right, so we do this and we get 10 times 2, which is what? 20. So you'd expect what? Not this, but you'd expect 400 plus or minus, not 40, but 20. So I just want you to notice, this is a very important law. It's called the law of averages. We'll go over it later. But I just want you to understand that as n goes up by a factor of 4, by times 4, from what? From 25 draws to 100 draws, what happens? The standard error for the sum goes up too, but it doesn't go up as quickly because the positives and negatives really cancel out. Is why it doesn't go up as quickly. It goes up as by the square root of 4, from 10 to 20. And what you'll see later is, yes, what you'll see later, that as a percentage of the number of draws, that means it's going down. Because as a percentage, watch, it's going to go down by dividing by the square root of 4. What do I mean? I mean that, where do we do it? 100 plus or minus 10? Relative to the number of draws. Like this is a 10% error. 10 over 100 is a 10% error. That's going to go down to where? 20, here's your error here. 20 over 400 is a 5% error. So with a bigger sample size, you're going to get a smaller percentage error. But as a sum, you'll get a bigger error. I don't expect you to see this right away, but it's an important law that we'll introduce later. Now, let me see, last thing I want to show you, and I know that your brains are full, but I want to give you an eye clicker question. And to do this eye clicker question, maybe I should just do it on this, because this is going to help you. And I'll just do this eye clicker question on this after you learn it. And this is going to be a relief, because do you like to compute the standard deviation ever? Who does? Okay, so this is a really easy formula for computing it when you just have 2 types of numbers. For all the gambling games where you either win something or lose something, or you're counting ones and zeros. When you just have 2 types of numbers, you can have lots of numbers in the box, but just 2 types, like you either win $7 or you lose $10, you know, something like that, or you're counting. What do? Let me show you. It's a really, really easy way to do it. You basically take the difference between these 2 numbers that are in the box, and then you divide it by the square root of the fraction of one of the types of tickets times the fraction of the other. And there's a proof online, but let's just see the idea. So here we go. Let's look at this. What am I talking about? First of all, you look at how spread out these tickets are from each other. That's going to increase your standard deviation. And they're spread out by what? 3. But another way to write that is the absolute value, and I don't care which direction you subtract them in, because you want a positive number, so you're taking the difference of those 2. So that's 3. You got a spread of 3 there. Now, it also depends on, that's going to be times, the square root of, what does this part mean here? What am I talking about here? Well, you have 10 tickets total. Do you see where that comes from? 5 and 5. You have 10 tickets. What fraction of them have this? Now don't pay any attention. They're just two different types of tickets. What fraction of them are this type? 5 out of 10. What fraction of them are that type? 5 out of 10. And that's your standard deviation. So the standard deviation of the square root of 1/2 times 1/2, which turns out to be 0.5, so that would be your standard deviation. All right. The square root of 0.5 times 0.5 is the square root of 0.25. What's the square root of 25? Square root of 25. 5. That's where I got this 0.5 from. I just did 0.5 times 0.5. Square root of 0.5. Okay, now let's do the next one. What's the difference between these two tickets? You can put the absolute, it's just 1 minus 0. Now, square root of, I want you to say in the denominator, how many tickets do we have total? 10. And we're multiplying these two. How many of them are of one type? 7, doesn't matter. And how many of them are the other type? 3. So this is exactly the same thing as saying 1 times the square root of 0.7 times 0.3, the square root of 21, 0.21. And that is about 0.46. You can do it really fast. Last one. Okay, maybe we should do this last one as an eye clicker. You want to do that? Yeah, okay, let me pull it up as an eye clicker. Get out your eye clicker so you can get credit for this one and think about it. And I have it on here. What is this example? There it is right there. This is the one. Okay. Now start the eye clicker. Where is my eye clicker? Is it being hidden somewhere? Is it started already? Do I have to start it? Okay, resume session. Where is my eye clicker? Searching for base. Well, meanwhile, think about the question. Okay, so think about the question right here. Do you want to do, can you see those choices? Do you need me to go bigger? This is the only one you're doing. I'm going to start it while you think about it. Sorry, it's that one. This says there's 34 of those and 4 of those. Do you want me to stop it? Anybody still working on it? All right, we'll stop it and let's see what the answer was. So the answer is like the difference between these two in absolute value is 9. So it has to be one of these. And it has to have 38 in both denominators. 34, so D is the answer. I'm curious if you got it. Cool, very good. Okay, so that's it for today. I'll give you double points for this, for coming. Never tell.